important. Hello and welcome back to Calculus 3. This is section 13.7 on change of variables in multiple integrals. Technically, this is U sub on steroids. So let's talk Calc 1 U sub for split second. So U sub is transforming the space, the region, from X domain to U domain, and then you do the integral. So if you have the integral, let's say from 0 to 3 of x e to the x squared dx, the way to integrate this is to say u is equal to x squared. So you are transforming the domain x into domain u. Du is 2x dx. We are going to add in over here a half and a 2. And also, we have to change the limits. So u1 lower limit is when you plug in 0. And then u2 is the upper limit when you plug in 3. So now, your new transformed integral is not going from 0 to 3, it's going from 0 to 9. We have the 1/2 in front. And then 2x dx is du, and then we have e to the u. So we have three transformations that are happening here. There is a transformation of the variable, transformation of dx, and transformation of limits. So now when we move to our Calculus 3 and talk about the change of variables on multiple integrals, which is the reason why I call this U sub on steroids, your domain now is not only x, your domain is x and the y, which means that you have two variables to transform, or three variables to transform. So you will have that substitution, like we had u equal x squared. You will have the transformation in what we call transformation equations. We have to transform the region, which is transforming the limits, and then we have to do Jacobian, which is actually transforming the dx, dy, dz part. So still the three things to do, but they are much more involved than what we had. So transforming the region is the first on our list. So what we are doing is we are taking, in general, we are taking the xy region of some kind and using the transformation function, transforming that into some kind of UV region over which we are going to integrate. So the transformation function is the one that will change that region. Now we can also do it the other way as well. So you can start in either one of these and use the transformation to go to the other. It's invertible. If it's a linear transformation, it's studied in linear algebra as a part of the course. But we also have a nonlinear transformations. So this is wider subject than what linear algebra has. So let's take a look at any of these problems. How about, well, we can do number 8, I guess, properly. Let's go with number 8. Now, this is only exercise in transforming the region. We are not concerning ourselves with transforming integrals, functions, or anything like that. We're just transforming the region. So region is given as a square. S equals all UV points such that U is in between 0 and 1, and V is in between 0 and 1. The transformation that we should use is given by x equals 2u plus v and y equals 2u. So now I'm going to draw the input for this problem, and that is domain S, which is a square, and this square is in the first quadrant. So I'm going to use, let's say, 3 squares. There we go. And this is my square in the UV region. So now UV region we have 4 line segments which we need to describe using these. So now we start with region number 1. Equation is v equal to 0 because it's on the u axis, and u is stuck between 0 and 1, and that will be our first line to transform. Let's go to blue. This is u equals to 1 because it's a vertical line, and then we have v between 0 and 1. Why we have to chop it off, because u equals to 1 is infinite line. It goes to negative infinity and positive infinity. So with this line v equals, we chop it off. So that's our line number 2. Line number 3, orange. This is definitely v equals to 1, right? So we have v equals to 1, and u is trapped between 0 and 1, which is what is cutting the v equals to 1 to the proper length. That's 3. And let's go green for number 4. This is u equals 0, vertical line u equals 0. And then we have the v, which is trapped between 0 and 1. So these are the 4 equations because we have 4 line segments. Guys, you can have a situation where you have 3 equations. Let's say you have a quarter of a circle, right? So you have 1, 2, 3. Or you have a triangle, for that matter, the same. 1, 2, 3, right? So you can have any amount of these, depends on what kind of shape you're starting from. Obviously, if you have a circle, you just have 1 to worry about. Or half a circle, that would be 2. You have the top, which is a semicircle, and the bottom, which is a straight line. So whatever you get, you should be able to write equations for each one of the line segments that bounds that space. Now, this is your space S, right? Space S that you can see over here. S is given in u and v, so I have u and v on my graph. So now I need to do these transformations. Now the issue is that this is a non-standard problem. Generally, your integral is given as x, y, z, and you are transforming it into u and v, in which case this transformation is given the right way. Now, since the target is given, and you want to go back to the original variables, we actually have to invert the transformation using equations, using the very simple equations. You just go and transform this y, so u is equal to 1/2 y, and then you plug that in here. So now you get your x equals 2 times 1/2 y plus v. This dies, from where v is equal to x minus y. The reason why I'm transforming this is because, again, I am given the target, the answer, and I'm looking what transformed into it. So I have to use the backwards transformation, right? Because transformation can go back and forth. So the transformation that we are actually using in this problem is u equals y over 2 and x equals x minus, and v equals x minus y. Okay, so now we are facing the standard situation. We have an equation. Let's go number 1, red. I have v equals to 0 and u is between 0 and 1. Well, v is given as x minus y equals to 0, from where I have y equals x. U is y over 2, so 0 less than y over 2. You're just plugging in, all right? And then when you multiply by 2 to get y alone, 0 less equal than y less equal than 2. So these are equations that you will be graphing on the xy graph. That's red. Let's go blue. Number 2, u equals 1, v trapped between 0 and 1. Okay, u is y over 2, so y over 2 is equal to 1, y equals to 2. v is given as x minus y, so 0 less than x minus y less equal than 1. And then we plug in y equals to 2, so 0 less than x minus 2 less equal than 1. And then we add 2 everywhere, so 2 less than x less or equal than 3. So now this is another set of your equations that we have to use. Next one is orange, number 3. It was v equals to 1 and u is trapped between 0 and 1. V is x minus y equals to 1 and u is y over 2. So to solve this one, y equals x minus 1, right? And to solve the other one, 0 less than y less than 2. So all we do, guys, is we take whatever the functions we have from the picture, from the graph, and we replace the transformation in it, and then solve for whatever form is appropriate and the best for us to graph in the future. The last one is number 4, which is green. We had that u is equal to 0 and v is trapped between 0 and 1. Our transformation for u is y over 2 equal to 0, from where y is equal to 0. Our transformation for v is x minus y less than 1, but y is 0, so 0 less than x less than 1, right? I'll just put over here y equal to 0 left. So we have this set of equations to graph. So I have transformed all 4 sides, and I am ready to graph the new region for the, now in this case it's actually the original region, but such is life. I don't have any negative numbers, so I'm going to focus on the upper half of the coordinate system. I'll use 2 squares as 1 unit. And this particular graph, guys, is going to be XY graph. Now, since I already see the green one, I'll graph the green one first. Y equals 0 is the x-axis, and I need to be on 0 to 1. So that's this much. That's it. That's number 4. So y equals 0 is x-axis, and that's the infinite line. But I'm supposed to cut it between 0 and 1 because of the condition on the right-hand side. The next one up, I believe, was orange. Yep. And the formula for that is y equal x minus 1. And y goes from 0 to 2. Now, x minus 1 is here, and it's a 45-degree line, so it's a line that goes like this forever. Y should be from 0 to 2. So it stops here, it starts there, so I'll erase the line and just draw the piece that I need. There we go. For this piece, I have the equation that I need, and I also have the the range because it needs to go from 0 on y to 2 on y. So it's tall enough, right? The next one I believe was blue, number 2. Y equals to 2 and x between 2 and 3. That's this much. Y equals to 2 is y equal 2 line infinite, and then we cut from 2 to 3 on the x. So we get that much. And the final one is the first one we actually did, which would be obviously this one that completes the shape. And now this is the region R. Cool? Now this was an exercise actually in inverse transforming something, because your problems start here and you say, I don't want to deal with this. Let me use the transformation t that was given before we flipped it around. Let me use transformation t to make this into a square and then integrate easier. But we don't care about that right now. We only care about, in this case, we only care about the process of transforming something. The process is very simple. You draw the image given the shape you have. You have transformation before you. Use the equations from transformation and transformation to come up with the new sets of equations. It's a very systematic process. So now that we know how to transform the region, let's start off a full integration problem, which always is the first step, has transformed the region. So problem 30 is something that has the integral over region R, and the region R is an ellipse. And you do not want to integrate anything around ellipses until you reach your 700 level coursework. So we have our region R given as xy, and now there is an ellipse there. So now if you take a look carefully at transformation, you would see that, first off, right, this works to be 3x everything squared, and this works to be 2y everything squared, right? Now you will see that this 3x is assigned to a variable, and 2y is assigned to a variable, which makes everything, very good effort, easier to deal with, because it transforms it into a different region. So let's see what we have. Transformation that it's given to us is x equals 2u and v equals 3y. Y equals 3v. So to transform the region, now if you draw this, you are going to get one continuous ellipse. So there is really not much in terms of the shape that we need to do. You can divide everywhere by 36 and get your x squared over 4 plus y squared over 9 equals to 1. And this gives you 2 units in x and 3 units in y. So your original shape is 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. So here is the ellipse in xy realm, and this is your region R. As I said, do not integrate over the ellipse. No, right? So what we are going to do is we are going to take this equation, 9x squared plus 4y squared equals to 36, and we are going to plug our transformation. So now transformation, let's do it red, is going to be 9. Instead of x, I have 2u squared plus 4. Instead of y, I have 3v. squared equals to 36. This is 36u squared plus 36v squared is equal to 36. Divide everywhere by 36 and you get what? Unit circle. Right? So this transformation was beautiful, right? We went from an ellipse and something that you don't want to integrate over even in your wildest dreams. We get to a unit circle which polar coordinates just cough up the answer in 2 seconds, right? Because your limits are 0 to 2 pi and 0 to 1. It's a rectangular polar integral, the easiest one you can possibly get in the calculus realm. So we go from absolutely worst to absolutely nicest in one transformation, which is the reason why we do this. So now you draw the unit circle. This is circle. It's just your eyes are terrible, so because clearly it's 1 everywhere. And this is the region S, the transformed region S, which would eventually spawn the integral, right? Blah, r dr d theta, the limits 0 to 2 pi and 0 to 1. Right? Awesome. This was way too short, so let's pick another one. 27 through 29. 28 it is. Double integral over region R. Now we'll come back to compute these actually, because we still have to transform the function. We still have to transform the dy dx part at the end. So we're not done, not even close. But at least we are working with regions. Region R is given as what? We have x that it's between 0 and 2. We have x less than y less than x plus 4. What is this? We have a transformation that takes x equals 2u and y equals 4v plus 2u. Well, I'm excited because this, all right? Well, guys, it's simple. Look, there's one equation over there, and there's another equation over there. It just looks crazy, but it's simple. So now, what do we do? Well, first off, we draw our shape. Now, it will be our R shape that we don't want. We use the transformation to transfer into S shape, and hopefully S shape is a joke, which is why I do all of this. So, where do I start? Well, let's see. 1, 2, 3, 4. 1, 2, 3, 4. Let's start with the functions first, right? So we have x equals y. That is going to be, and I'm going to use construction lines for this. So I'm going to use a very thin black line over here and draw y equals x going like this forever, and then y equals x plus 4 is a parallel line that goes through 4 on y-axis, so it's going to look like this. So these are my construction lines for y equals x and y equals x plus 4. Now they're very thin because they're infinite, right? I have to chop them off between 0 and 2. So if I chop this off at 0 and 2, x equals 0 is here, and x equals 2 is here. Oops. Now I have to switch back to the... See, so this is my x equals 0 and x equals 2. So this is how much I need from the original. Now this is our region R. Again, I have 4 sides, therefore 4 equations, then 4 line segments to transform. Number 1, red. So for red one, I have the equation y equals x, and x is stuck between 0 and 2. Number 2 is going to be blue, and I have that x is equal to 2, and y is stuck between 1 and 5. No, lied. 2 and 6. 2 and 6. Next one is number 3, orange. Y is equal to x plus 4, and x is stuck between 0 and 2. And the last one is green, number 4. X is equal to 0, and y is stuck between 0 and 4. So here are my four line segments. I wrote out the equations. I hope you are now coming to school with a pack of colored pencils, because obviously you need it. Now you can get that in the kids section. It's a kids / Calc3 section at Staples. Yeah. Now we know why A is inbound. So we have these. I'm going to start with the red one, number 1. I write y equals x, and x stuck between 0 and 2. Plug in stuff. 4v plus 2u, that's y, equals to x, 2u. Well, that's 4y equals to 0, y equals to 0. On the right hand side, x is 2u, so 0 less than equal than x, x is 2u, so 0 less than equal than 2u, less equal than 2. Divide by 2 everywhere, 0 less than u less than 1. Here's the first set of equations. Number 2 is blue. By the way, this x-axis is x-axis, and the y-axis, this is the... Oh, yeah. That's a v. I should say it's early in the morning, but then it's 11:36, so... well, it's early somewhere, okay? Thank you. Blue equations, x equals to 2 and y between 2 and 6. So x is given as 2u equals to 2, u equals 1. Y is this long, so 4v plus 2u less than 6. But guys, we know that u is equal to 1. Right, we have it here. If u is equal to 1, we have 2 less than equal than 4v plus 2 less equal than 6. You subtract 2 everywhere. 0 less than 4v less than 4. Divide by 4 everywhere. 0 less than v less than 1. So there's another set of the equations. These Tetris pieces are hilarious. Number 3. No, 3 is orange. Y is equal to x plus 4. 0 less than x less than 2. Y is given as 4v plus 2u is equal to x is 2u plus 4. So u's cancel, and then 4v equals to 4v is equal to 1. X is given as 2u, so 0 less equal 2u less equal 2. U is stuck between 0 and 1. There's that. And do you already see that this is a square? 0, 1, 0, 1? We have enough information. for the square 0, 1, 0, 1. I am going to do 3 because remember what I said yesterday? I have been labeled to be the best in Galaxy, so I have to, you know, make sure that that stays as is. But you already see it's a square. So x is replaced by 2u in a transformation. There we go. U is 0. And then over here we have 0 less than 4v plus 2u less than 4. But u is 0. Look at the, right, over here. So since u is 0, this becomes 0 less than 4v less than 4, which is v is between 0 and 1. And that's the last set of things that we need to transform. And now when you draw this on your UV graph, your region is a square. And this is region S. So we took that parallelogram that we had in R and transformed it using this transformation into a square. And then you might go, yeah, so what? Well, now you're integrating over a square. You're not integrating over a parallelogram, which means your limits are rectangular rather than having functions. So maybe you want to do some rudimentary algebra to save up on calculus integration with limits that are functions. That, I don't know, or maybe you don't. The main reason why you do transformation of integrals is when you have the integral that you cannot integrate. Let me start from the fact that it's pointless, because computers solve these things without you sitting there for 37 minutes transforming the region, all right? But as soon as you go over that hump and you make, you know, peace that we are honoring our ancestors, because this is the way it was done in school 200 years ago, I'm serious, they had no Mathematica in 1800s, right? Right. So the only way to integrate this in 1800s was to actually crank this thing, right? So what happens when you see the integral and then you have some function limits up there? Those are not zeros, those are some functions, g and h. And then you have your e to the, you know, x and then squared, and then you have to change those limits, right, with the x here, and then dx and then dy and so on, right? And then these functions make everything worse. So let's finish this problem. Let's finish this problem. So now what I'm going to do is I'm going to write the formula that is a complete transformation of everything that you have to do. And that is this. So the double integral in region R with a sum function of x and y dA is going to be now the double integral over region S. S stands for easy, right? There is an S in the word easy. We have F, which is each x and y is transformed with the transformation UV. Times the determinant of the Jacobian, and the Jacobian is partial x, partial u, partial x, partial v, partial y, partial u, partial x, partial v, no, partial y, partial v, there we go, dA. This is definitely something that you casually leave on a napkin as you are leaving the restaurant. And if you get caught doing that, it's even more fun. What do we have? Our transformation that we did so far deals with this, to get you the limits of the integration. We are left to transform the function, and then we are also left with transforming the dx dy part. So let's go and deal with those. So my problem 28 was the double integral r, I believe it was x squared y, right? Yeah, x squared y dx. dA, sorry. We have the transformation which was given as x equals 2u. And y equal 4v plus 2u. So your f of xy is x squared y 2. Plug in. And transforming the function is done. Yay. So now my f in terms of u's and v's, actually I can just say uv, is going to be, instead of x squared, I get to put 2u squared, and instead of y, I get to put 4v plus 2u, and then I get to work this out. So that's 4u times 4v plus 2u. So my new function that I have to put in the integral, this is your substitution, is going to be 16uv plus 8u squared. That goes here. So we transformed the region. That is the 4 calculations we had in colors. And now we transform the function. The next piece is to compute the Jacobian. Jacobian is what it is. You remember the way it's set up, and then you know how to work out the diagonal minus the diagonal, right? So Jacobian of uv is the partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. There we go. And you find determinant for that. Yes. For u squared. What? So 4 times 4 is 16, and then 4 times 2.
2u squared. 2u squared times 4u is x. Squared. U squared x. The u is squared.
Ah, there is a square over here. Why don't you say so? All right. So there we go. Ah, that's a cube. Yeah, well, that will just change everything. Obviously, it's you know, it's -4 on the test. Guess who's not taking the test on Tuesday? I can't care less whether there's a square there or not. But good thing you do. That means you're going to do very well, right, with Jacob over there. Without the colored pencils. All right. So, where was I? Oh, yeah. Okay. So now, Jacobian, we have our transformation, right? Let's use the transfer. Let's do the... I haven't used orange enough in my life, so here we go. Partial x, partial u, that's 2. Partial x, partial v, that's 0. Partial y, partial u, that's a 2. Partial y, partial v, that's a 4. 2 times 4 is 8, minus 0 is 8. Jacobian is 8. Is Jacobian always going to be a number? Hell no. For the linear transformation, which is what we have, yes. If I go in and I say, no longer a linear transformation, well, your Jacobian is no longer a number. It's going to be a function, right? Because when you take a partial derivative of that puppy right there, you are going to get summer sale. Remind me later. I still don't know what they're selling. I scoped one of these Nigerian princes selling money. Anyway. Am I ready to put the integral together? I hope I am. I have double integral over region S of my FUV with the Jacobian UV with the dA. I should be able to plug all of this in now. I'm integrating over a square, 0, 0, 1, 1, and then immediately it doesn't matter whether you do du, dv, or dv, du, because it's a rectangle, right? Square. It's a rectangle, so the order really doesn't matter. They're really persistent. I said later, that was like 10 seconds later. So now they get an X on that. Patience, young Padawan. We have now function. That's 16u squared v plus 8u cubed times 8. That's our Jacobian. And now we simplify this a little bit. Well, we don't simplify it, we just kick 8 out. So I'm not going to do it. I'm just going to kick 8 out and then integrate in respect to u. I should have done v. I'm switching this. V first, u last. Because when I integrate v, I get to cancel 16. If I integrate u, I get 16 over 3. I know I will eventually get 16 over 3, but that is so much better than what I wanted to do in life. Nice. Factor out 64. You factor out 8 from here, and this 8, that gives you 64. That's such a life quality improvement. Thank you. 2u squared v plus u cubed dv du. There we go. Nice. 64 integral 0 to 1. Integrate v, you get v over 2, cancels with this one, so that's u squared v squared plus u cubed v. Computed from 0 to 1, and you still have du to deal with later. When you plug in 1 and a 0, all you get is 64 integral 0 to 1 of, so all the v's are out, u squared plus u cubed. du. Now that's 64 times. You have your u cubed over 3 plus u to the 4th over 4. That's a u. From 0 to 1, from where all you get is 1/3 plus 1/4. Now that's going to be 7/12. So it's 64 times 7 over 12. Cancel by 4, you get 1/6 times 7 over 3. 16 times 7, 71, 40, 112, right? Over 3. That's good enough. 112 over 3. Now, I'm going back to the setup of this problem, 28. I'm going to discuss the region R, which was 5 pages ago. There we go. It was this. So integral for something like this would be x squared y, and we have to use dy, dx has to be anchor, it will be 0 on 2, and over here you have from x to x plus 4. Right? And the next one is the square 0, 1, 0, 1, 1, 1, which is the integral of 8 times, no, 64, what was that thing? 64, so 0, 1, 0, 1, 64 in front, and over here we have some combination of u and v, u squared, v squared, no, 2u squared v plus u cubed. And I wanted to do dv first and then du. There we go. If you are, as you study this and you go, why? Well, that's why. There you go, that's why. So you have a choice of integrating that or integrating that. Now look at the limits, right? The second part of this is a completely pointless problem. It was just mathematical gymnastics for you to practice this because you can integrate both of these, right? And I actually think that you would rather pick the one on the left and do 2 pages of work so you can do the one on the right, which should be, right, a sane thing to do. But remember that there will be cases like that ellipse problem, which I haven't done yet. Now that problem you can't integrate in its original state. You will only be able to integrate that problem in its transformed state. So that's the big difference. This is only useful when either considerably reduces the amount of work after investing 2 pages anyway, or the other integral is not possible, or it's elliptical integral, in which case, yeah, fun, right? So now I want to finish off the problem 30, which is the problem that we have for our ellipse problem. So back to 30. What we know now is that our region S is the unit circle. We had our transformation T. It was so long ago. It was 4 pages ago. Let me just remind you that we haven't started the triple substitution yet. No, I'm serious. It's all 2 variables. It's xy going to uv. Then you have xyz going into uvw. This class will never end. This is it. There it is. X is equal to 2u and y is equal to 3v. We were supposed to integrate over region R x, y, dA. So what do we have now? We want our integral over region S, and our xy is going to be function in uv, and we're going to have our Jacobian uv, and we're going to have dA. All right, let's do it. Function in terms of uv, not a problem. X is 2u, v is 3, y is 3v. Jacobian, I haven't done that yet, but partial x partial u, that's 2. Partial x partial v is 0. Partial y partial u is 0. And then the other one is 3. I'm going to put dA over here. So when I solve the determinant, it's 6 times other 6 from here is going to be 36 in front of double integral uv dA. And this is when I go S is a unit circle in UV. Are you going to do trig sub? No, you don't want to do a trig sub, right? You want to do polar. So it's a joke, right? Okay, polar it is. So that's going to be 36 integral 0 to 2 pi and 0 to 1. That's a unit circle in polar coordinates. Careful. You are switching to polar coordinates. Your u is no longer u. Your u is r cosine theta. Yes. And your v is r sine theta. So I'll just put these thingies over here and say this is your u, this is your v, because polar. Your Jacobian is out as 6, and you have your r d theta. So now you have your 36 double integral 0, 2 pi and 1 r cubed, and now you have your sine cosine. You know what I'm going to do? I'm going to make that into a sine 2 theta and steal 2 from 36, so now it's 18. Bueno? Yeah, a little bit of trig. Maybe I write it in orange on the side because it's so much fun. Sine 2 theta is 2 sine theta cosine theta. You know why I do this? So I don't have to do u sub. Because if I have sine and cosine, then I have to go eventually u equals sine theta, cosine, the du is cosine theta d theta, and then I have to do that. But if I compress all of this into a single sine, well, yeah, then it's just, you integrate sine, you get the negative cosine over 2. Woo, right? Happy. At this moment, you probably realize why I'm happy all the time. It takes very little to make me extremely happy. It's just that transformation, the orange one. Like this is a dose for the day. Good luck trying to ruin it. You can. So we have 18 integral 0 to 2 pi. We have r to the 4 over 4. Sine 2 theta is the constant. We have d theta, and this thingy goes from 0 to 1, which gives us a quarter. Quarter outside is going to give us 9/2. Nice. Integral 0 to 2 pi, and then I have my sine 2 theta d theta. Now that's gonna give us 0. Rip, right? But such is life. 9/2 negative cosine 2 theta over 2 from 0 to 2 pi. That is negative 9/4 outside, right? You take that negative half from cosine. And we have cosine of 4 pi, which is 1, minus cosine of 0, which is 1. So the answer over here is 0. When I was in high school, I asked the teacher, after solving whatever algebraic thing we had, equation, we got x equals 0, I said, what is the point of solving this for 15 minutes if you're going to get nothing at the end? The answer was swift. Get out. I said, all right. I guess I'm playing soccer for the rest of the day. Which is actually what happens. You get kicked out and you go and play soccer because the school is not for you. Obviously. Okay. That's 2 variables. Should we take a break or just go and do the 3 variable and then be done? Let's do 3? That's the spirit. All right, so the textbook software is asking me this. They didn't leave me with the option to click yes. Because I would so much love to do that. It's like the only thing I can do is to click this. Oh, I have to solve a puzzle. Get the cars. Well, that's a bus, so no. But there's a car right here. Let's click it. What is this? Oh, there's a car right there. This is not a car. Check new images. There's a bottom left. See, wow. There's a truck. That doesn't qualify. Maybe there it is. I don't know. It qualifies. Wow. I think we ran out of the options. Nice. I want to do this again. You can't. Oh my God. There we go. Well, I guess now we have to do 3 variables because we're done with our. There you go. Look at the formula. It's the same. It just has 3 functions and 3 variables, and Jacobian has 3 lines instead of 2. It's the same thing. Just expand it in W realm. This is definitely the formula you want to leave behind. I guess let's write this. So we have our triple integral over region D with a function x, y, z dv that needs to be transformed into the triple integral. They are using s again. And now f. We need to transform this f using the transformation, 3 transformation functions, g, h, and p. So g, u, v, w, h, u, v, w, it's a definition. P, u, v, w, there we go, times the Jacobian, u, v, w, no, we're going to write the Jacobian in, so we save a little bit of a forest. Partial x, partial u, partial x, partial v, partial x, partial w, partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, partial z, partial w. What? You think my job is easy? I just said partial 18 times. This is 19th in the same minute. There's the reason why I make $5 an hour. All right. Now we have our definition over here. And our transformation to follow this is x equals g uvw. Let's switch the display. H uvw and p. No, z is function p. uvw. Every time I write this, I'm trying to picture, let's say, a Rutgers student at the lecture hall who zoned out while the professor wrote this on the board and then just tuned in and saw it for the first time without any concept prior to that, with other 250 students around when everyone looks like, yeah, this is easy. At 2,000 per course. It's an exam on Tuesday, right? All right. So, what, 2x2 problems were 40 minutes each on 2 pages? This obviously should be 2.5 times that long, right? Because look at Jacobian, right? Now, you have a shape that it's bounded by functions on sides. And each one of those that are half a sphere or a paraboloid or a plane will be transformed in the same way. You are looking at the classroom you're sitting in, and this is a box, and this box has 6 sides. If you haven't been to Ripley's, believe it or not, if they're still on operation in Orlando, let's say, they have a room that is really awesome. They put in a pool table, right, with few of those billiard balls on it, which is clearly flat. And then they built the room around it. They made the floor on an angle so that one side of the table is actually in the level of the floor, and the other side is like almost down to where the floor actually would be. And the entire room has the walls that are crooked and the ceiling is off. So when you walk into that room, and I've seen people stumble because they immediately lose their, like, now I'm a video game veteran, so for me that's nothing. But some people really just can't walk through that room because their head spins right away. If you ever go to Orlando, you should check that out just for that one room. The freakiest thing of all is that because the floor is slanted and the walls are slanted, it seems that the billiard table is slanted. Your brain adjusts to make the floor flat and walls, 90 degrees, because that's what you're looking at all the time, right? Your house and the store and school, right? Everything is 90 degrees. Over there, you can't find 90 degrees if you try. But the fun part is that the billiard balls that should be obviously always to the side that is touching the floor, because the table actually looks like this because everything else is actually the billiard balls work just fine, right? So there is the example of the, well, space is not transformed obviously because you can't mess with gravity, but the interesting thing is that there is a linear transformation between that room and this room. So you should be able to take a corresponding linear transformation and transform the room that it's with those angled walls and angled ceiling and angled floor right into a room that it's a box. So how do you do that? Well, first you define each plane, right? And it's not just a flat floor. They actually put in the stairs and stuff like that. So you actually really have to pay attention when you're going to that room. It's a really, really interesting room. So now, to transform the region in 3D, you take each plane, you plug in your substitutions, you work through the whole bunch of algebra, and then you have your transformation 6 pages later. Then you do the same thing. You do the Jacobian, and then you replace each x, y, and z with what these are. Now, your troubles are not over after all that work, because your integral might end up being spherical integral, right? So you have to really work out that transformation, and hopefully it ends up being x, y, z. So let's see if we can do, some of this stuff. Yeah, I know, man. I would do it too. Ooh. So problems 43 and 44 are absolutely diabolical. Let's go and see one of those. It's a learning experience, right? That's why people don't sign up for. I told you guys are 0.5%, right? How's it feel? You had people protesting to get into 1%. Now you 0.5%. You are twice as good. And yeah. You can do this at the beach. You stream it. Sitting at the beach. So the triple integral of that's something. No one. The rest are ninjas. I checked the enrollment yesterday. It's 33. We started 33. We still have 33. Ninjas are sitting at home and watching this. Let's see. Come on. Watching 0. All right. Nice. No, 1. Oh no, that's me watching myself. There we go. All right, great. I know. So yeah, ninjas are sitting at home. They will watch it later. So there you go. So we are transforming this. Region D is bounded by the paraboloid, but this is elliptical paraboloid. Yeah. 16 minus x squared minus 4y squared, you see? It's not the same number in front of x and a y. So it's ellipse. Do you want to integrate over it? Hell no, right? Bottom is z equals 0. So what you have is elliptical paraboloid. Guys, that's the umbrella. Remember, I gave you the idea. You make it into elliptical umbrella for 2, right? Sell around Valentine's Day, obviously. I quit. Guys, I have these ideas. I should pursue that, and that's it. You're on your own. They'll bring someone in for your exams next week. So you have this elliptical umbrella, and then the floor, z equals 0, flat on the bottom. So you only have 2 things to worry about, bottom and the top. Nice. So we don't have to transform 6 sides of a box. The transformation they want us to use in this case is x equals 4u cosine v. Y equals 2u sine v. And z equals to w. Yay, cylindrical. So here's your 3D problem. Great. Transform the region. We can actually draw this region. It's okay. Right? You draw some kind of a ellipse over here, and then the hat on it, and you put these x and y axis in, and there's your hat, I guess. So now this is your region D, right? The object D. Z equals 0 is the floor, right? It's the xy plane. So that's this piece. So that's z equals 0, and the top piece over here is red. No, I'm gonna use blue because complementary colors. Yes, you get to learn some other stuff than math in this class. Blue is also primary color, and if you mix it with yellow, you get green. If you mix it with red, you get purple. See? Very good. I'm going to put that on the next test, so let's see how that goes. Replacement question. So you get to do that or the triple transformation over there. You see everyone telling color theory at home. It's like, okay, he said this. It's on the stream, so it must be true. Yes?
Why is equal to all?
It's not a circle, it's ellipse. Because when you plug in 0 over here, right, these two puppies go on this side, divide by 16, you get the ellipse with the radius of 4 and 2. So, and we can actually see those 4 and 2 here, but yes, at 0. All right. One thing that I always wanted to say, but I never did before, so here's for the first time in Calculus 3, Autobots transform, right? Let's go. Transform. I love Autobot Transformers. It's just, I grew up with it, so if you think it's cheesy and whatever, you shouldn't be in this class. It's Calculus 3. Technology and sci-fi should be your primary concern for all of you. Alright, so now we have 16 minus x squared minus 4y squared. We have to transform that, and we have functions that we plug in. That's our transformation. So let's go with the easy one, which is number 1. That's the floor. Z equals 0. So number 1, z equals 0. Since z is w, w equals 0, and we are done. I'm going to box that equation. Nice. And then I'm going to do the same thing for the blue now. Number 2. Is z equals 16 minus x squared minus 4y squared. Guys, I'm going to replace x, y, and z from transformation for x, y, z in the equation, and then deal with algebra. Z is w. There we go. 16 minus, instead of x squared, I have 4u cosine v squared minus 4 times, open parenthesis, 2u sine v, close parenthesis, squared. Alright, deal with it. 16 minus, I have 16u squared cosine squared v minus 16u squared sine squared v. We can factor, 16 minus, and now we factor out 16u squared, which gives us cosine squared v plus sine squared v. And that is nice. So now we have w is equal to 16 minus 16u squared. Bueno? So we are done as long as we know what this is. What is this? Well, that's the domain. So if I want to draw this shape, because guys, I need to know what this is, and the reason why I'm doing this is this is going to give me the limits for my triple integral as I'm setting it up, right? So what is this? No, what is this shape? To graph it, to draw. What is this? It's a parabola, right? It's a parabola. So now I have my space. This is terrible. And this is U, V, W. It is UW parabola, and when u is 0, the w is 16, right? So I have a parabola on u which will go this way, like that, riding the u-axis. Now it's going to hit w equals 0 plane and give you the bottom of that. It's a tunnel. It's a mailbox. Thank you. It's a mailbox. It's a tunnel. Right? That's what it is. This is a terrible drawing because it shouldn't curve that way, but I don't know. Maybe it's a little bit better this way. I don't know. Thank you. It's a mailbox. Yeah, this is still bad. It has to pass. It has to be on U right there, like this, and then go through 16. So, oh wait, I should do it on the x-axis.
Is it just one sheet or is it hollow?
It's yeah, it is. It's hollow inside. Mailbox. It's a tunnel. So, well, it's solid for the volume. It's solid. It's just this is the outline of it.
When does it hit V? Where?
Now I just need to see what's happening with V exactly, because does it go from where to where it goes in V? We have W equals 0. That's the floor, and the top is W equals 16 minus 16 U squared. So the only thing I have to figure out is what's happening with V over here. V, should we say that V is between 0 and 2 pi? I think that should be it for this one. Cos trig. Let's see what we get when we do the integral. So now the new integral over here is going to be the reason why I want V to be 0 to 2 pi is because it's trig over here. So we'll see that. Triple integral. Our function was a z, so that's just w. Now we need our Jacobian. Jacobian is going to be like this. Okay. Partial x, partial u, that's a 4. Partial x, partial v, that's 4u sine negative 4u sine v. Partial x, partial w is 0. So that's the first row. Then we have a partial y, partial u, that's a 2. Partial y, partial v is 2u cosine v. And 0. And the last row is 0, 0, 1. And we have dv, and this is region S, which is our new. In this case, like for 2, variable substitution, we said S easy, but because S wasn't there. In triple integral, S stands for hope. There we go. Yeah, Superman and Clark Kent are not reacting on this one. That's not good. All right. We need the determinant for this. Observe a 0 and a 0 there, so those die, right? This is the only one that survives, right? So we have a triple integral over S. That's a W there, and if I pick 4, let me just draw this out. So if I pick 4, right, you have this. Oh no, actually this survives too. All right, let's see. So what do I have there? 2u cosine v. Okay. Then if I pick this one, I have minus 4. And then if I pick the last one, that's a 0, 0, so that's where everything dies. Whee! Nice. dv. So the limits for this shape, we anchor this dv, right? dv, the lowercase v. If I anchor this, it doesn't actually matter because it's a rectangle. What am I talking about? The domain over here looks like this. That's our v, that's our u. So it doesn't matter whether you go u, v, or v. Okay, got it. So triple integral w 2u cosine v minus 4 dw dv du. U goes from what u goes from? When w is equal to 0, from -1 to 1. Because our formula is 16 minus 16u squared, and when w is equal to 0, because that's on the floor, as you can see. Oh no, that's a v. Yeah, this is supposed to be u, right? And this is supposed to be v. Kill me now. All right, but that's okay. We fixed it that way. Not ideal way to fix it, but we fixed it. So we have 16u squared is equal to 16, u equals plus minus 1. So that's why the limits on u are plus minus 1. Limits on w, most inner one, is easy. 0 to the w function, and w is the top. So that's 16 minus 16u squared. And then you have the v, we said 0 to 2 pi. I'll put this here like this, so it's easier to understand. So w equals 0, and w equal 16 minus 16u square. 0 equals 16 minus 16u square. U equals plus minus 1. There we go. Equal to, boom. Integrating this should not be an issue. Wow. That wasn't that bad. I mean, it could have been much worse. You get a box with 6 sides, you have to transform each one of them. We only had 2. I give you half of this problem on a test and the other half of this problem on the final. Yes?
Why is 0 to pi?
The limits for trig, for the full period.
Isn't it half of the cylinder? Okay.
What do you mean half of the cylinder?
Like
It's the full cylinder, because your limits for the ellipse, right? When you do parametrization for ellipse or a circle or something, you have your theta or parameter t, whatever you want to use, 0 to 2 pi. That parametrization will be important for Monday as well, right? That's parametrization. It's right there. Oh, I'm done. So we'll reset this for chapter 14 so we can do something easy, right? But this is easy, it's just so long and way too involved.